right, on to number 4. Take a moment, make sure you've read it carefully, and let's go through it. So we are looking for the total mechanical energy here. There are several ways you can do that. Remember, mechanical energy is equal to Ke plus Pe. And since it's a horizontal spring, we're really just talking about elastic potential energy. There's no gravitational potential energy involved. This is one where some strategies are going to be helpful here. One thing you'll notice is if you look at the answers, they're all exactly the same. The only thing that's changing is the time interval that they're looking at. So what we should do is talk about why they want you to find the slope of the curve at a certain amount of time, and then talk about why D is the best answer. Before we do that, notice that these are increasingly smaller time intervals. The first one is 1 second, the next one is 0.6 seconds, the next one's 0.2 seconds, and then this one is about 0.1 second. So why is a shorter amount of time the best slope to use? I'm going to try to show you on this graph and remind you of a few things. So if we want to look at the slope for letter A, like it says, between 0 and 1 second, that would look something like, I'm going to use my ruler here actually, that would look something like this. I don't know how well you can see that, but it's not a very good fit to the line. Here it goes above the line, here it goes below the line. And because this is a sinusoid, or a cosine graph, if you know what that means, it doesn't fit very well. It's not straight at any point. Why do we want this line to exist at all? Well, as you know, the slope of position is velocity. So we want to get the slope as close as we can to match the slope of our actual graph itself. So the best thing to do is to only look at the slope over a tiny, tiny interval. You might remember us doing that in graphical analysis. I'll show you that in just a moment. So they're all the same question. We want to find the velocity using the least amount of information as possible so that it matches the shape of the graph as best we can. On this one, we can very quickly then jump to letter D. So I've got a spring mass system here, and you can see that its position oscillates up and down, very, very similar to our graph from the question. And remember, we can take the slope of a position graph and get the velocity. I want to show you why narrowing how much time we look at is actually going to be super helpful here. So if I just straight up say, okay, apply curve fit, look how bad of a fit that is. Obviously, it's like a straight line. Let's narrow this a little bit so that we're looking at just the backside of one of these graphs. So if I go here, you'll notice that I'm taking from basically the top to the bottom of where the spring is going from a maximum position to a minimum position. And you can see that my slope here is negative 0.4 or something like that. And what you're going to see is that the slope gets closer and closer to the real line when I take fewer points into account. So notice it gets a little bit steeper, a little bit steeper, a little bit steeper. I think I can go one more. Yep. And that's going to give me, notice it's a bigger value for V, that's going to give me a much closer value for what I want. Additionally, remember we can use the tangent tool. That's something we've spoken about before. If you're in calculus, you probably know all about that. But what the tangent tool is doing is it's just taking the point in front of it and the point behind it. It's not taking into account all of the points on the line. So you can see there that's pretty darn close, that value there, to what we got a moment ago. So anyway, we want to take just the tangent to get the velocity, and then remember that will give us the kinetic energy to solve this one. So that's it for number 4. Thanks, folks.